Now we shall see about the various symmetry elements. Plane of symmetry is the plane which divides the molecule into two equal halves which are the mirror images of each other. So plane of symmetry is an imaginary plane which is bisecting the molecule into two equal halves which are the mirror images of each other, that is always denoted with the symbol sigma. So just look at this mesotartaric acid molecule. This has a plane of symmetry. This has an imaginary plane here which can divide the molecule into two equal halves, and these two halves are the mirror images of each other, and this imaginary plane is called plane of symmetry. Now center of symmetry or inversion center. So center of symmetry is a point in a molecule from which if you travel in opposite directions to equal distance, you should meet with identical groups. So usually the center of symmetry is the central point of the molecule. So in this molecule 2,4 dimethyl cyclobutane 1,3 dicarboxylic acid, this is the central point of the molecule. From this central point, if you travel in this direction, we meet with carboxyl group, and if you travel in the opposite direction in the same axis at the same distance, we are meeting with another carboxyl group. So when we travel from the central point of the molecule in opposite directions, we are meeting with identical groups at identical distance. So if you travel in this direction, you meet with methyl, and in the same axis if you travel in the opposite direction, the same distance, you are meeting with the same methyl group. So you are meeting with identical groups at identical distance when you travel in the opposite direction from this central point. So this molecule contains a center of symmetry which is otherwise called inversion center, that is always represented with the symbol small I. Proper axis of rotation. So it is an imaginary axis which passes through the molecule. About this axis, when you rotate the molecule to an angle theta, if you are able to produce an equivalent structure, then the molecule is said to have a proper axis of rotation or rotational axis of symmetry. So it is an imaginary axis which goes through the molecule, about which when you do a rotation for angle theta, you have to meet with an equivalent structure. So then this imaginary axis is called axis of rotation, proper axis of rotation or rotational axis of symmetry, which is denoted with the symbol Cn. So the angle to which you have to rotate to get the equivalent structure is theta. So 360 by theta will give you n, which is called order of rotation, which means the number of times you will get equivalent and identical structures when you rotate the molecule for 360 degrees about this rotational axis of symmetry. So rotational or proper axis of rotation with the order n is called n-fold axis of rotation. So let us see how the molecule can be rotated about this axis. So about this C2 axis, the molecule can be rotated. So when it is rotated 180 degree, we get the similar identical structure. So this is inversion center. So when you travel in the opposite directions, let us see it once again. So about this axis, we are rotating by one full rotation gives two similar structures. And this is inversion center. In case of plane of symmetry, we did only one operation, that is the reflection operation. In case of center of symmetry, we did only one operation, that is traveling in opposite direction from the central point of the molecule. In case of rotational axis of symmetry, we do only one operation, that is rotation about an angle, about an axis. In case of improper axis of rotation, we have to perform two operations. One is rotation about an axis which passes through the molecule. Then reflection about a plane which lies perpendicular to that axis. Let me explain that with an example. I have taken 1, 2, 3, 4 tetrachlorocyclobutane, which has the chlorine atoms in the adjacent carbon atoms in the opposite side. So here the CCl bond is upward bond, that is beta. Here the CCl bond is downward, that is alpha. Here it is CCl is beta and here it is alpha. Now let us perform a rotation about an axis which passes through the center of the molecule. So through the center there is an imaginary axis about which I am doing a 90-degree rotation. After doing 90-degree rotation, this carbon comes to this position along with this hydrogen and chlorine. So after 90-degree rotation, we will have this CH bond here and this alpha CCl bond here. After 90-degree rotation about the axis that goes through the center of the molecule, we are going to perform a reflection operation with respect to a plane that contains the 4 carbon atoms. So there is an axis that goes, that is, let us imagine it is perpendicular to the plane of the screen, and the plane is just on the screen. So we have done a rotation about 90 degrees. Now we are doing a reflection with a plane that contains the carbon atoms. So when we do a reflection, what happens? This chlorine in the alpha side comes to the beta and this is reflected to the alpha side. So now we will have chlorine in the beta side and hydrogen in the alpha side. Now you can see this structure is equivalent to the original one. So a rotation followed by reflection gives a structure that is equivalent to the original, and this operation, rotation followed by reflection operation, is called improper axis of rotation. And if you are rotating the molecule by angle theta, then 360 by theta will give the order of improper axis of rotation n. Let us see that with an animation now. So I have taken the three-dimensional structure of the molecule. All the yellow balls are all these yellow balls are chlorine atoms and the white balls are hydrogen atoms. So we have chlorine in the beta side now. So here it is, now it is down, the CCl bond is downwards. And now if you rotate the molecule by 90°, this yellow ball will move here. And then if you do a reflection, this yellow will go up and the white will come down. So in our earlier discussion, I have told you that for a molecule to be chiral, it should be asymmetric, which means it should not have any of the four symmetry elements. But now we have observed that it is enough if a molecule does not possess the three symmetry elements sigma, I and Sn, and the absence of proper axis of rotation is not mandatory. If all the four symmetry elements are absent, then we call such molecules as asymmetric molecules. But we don't expect the molecule to be asymmetric. It is enough if it is disymmetric. So disymmetric molecule is one which lacks sigma, I and Sn. Therefore, asymmetry is the absence of all the four symmetry elements. We don't expect an asymmetry in the molecule. It's enough if the molecule is having dissymmetry, which means it should not have the symmetry element sigma, I and Sn. Now, the plane of symmetry sigma is equal to S1. Rotation to an angle 360° followed by reflection will give the same structure. So we can say sigma is equal to S1, and inversion center of symmetry I is equal to C2 rotation followed by sigma I reflection. So it is equal to S2. So now dissymmetry is not, can be defined in another way, that is absence of Sn, improper axis of rotation, because sigma is S1, I is S2, and all other Sn operations in are coming under this Sn. Therefore dissymmetry is the absence of Sn. So for a molecule to be optically active, it is enough it is not having Sn. At the same time, the asymmetric molecules also are optically active, as they also do not have Sn. Therefore, from all our discussions, we have understood that for a molecule to be optically active, presence of asymmetric carbon is not a must. Presence of chiral carbon is not the most important requirement. Instead, the molecule has to be dissymmetric. The molecule should lack Sn, should not have sigma, I or any other Sn operations. So lack of Sn is enough for a molecule to be optically active, which means the molecule has to be dissymmetric. And we can understand that from these molecules, some allenes with suitable groups, biphenyls, spiranes, these are some examples for molecules which are showing optical activity even in the absence of chiral centers or chiral carbon atoms. Therefore, for a molecule to be optically active, we need not look for an asymmetric carbon or a chiral carbon. It is enough if we look for the dissymmetry in the molecule, which means the absence of sigma, I and Sn, or simply we can say lack of Sn in a molecule makes it optically active.